Hey everybody, so as promised, I'm going to show you guys the math that underlies these categorical or dummy variables that we went over in the last Excel video. So last time in the Excel video, I showed you how to implement them in Excel, but it's useful to really understand the way that these variables work in the algebra, because then you can start doing pretty cool things with your regression equations. So I'm going to motivate this discussion with an example of house prices, which we've used a lot in class. So think about the question, what are the determinants of house prices? Now we'll just use a simple multiple regression example with one dependent variable and two independent variables. So of course, based on that research question, our dependent variable y is house price right here. So your data set in Excel might look something like this. You'll have a list of house prices for your dependent variable. Now, we've talked about in class, what's a really important determinant of house prices? Well, probably the size of the house. So our x1 variable, which is going to be a numerical continuous variable, x1, square footage, is right here. So I'll put that right next into my Excel spreadsheet next to my dependent variable. And then we're going to use air conditioning as an example of a categorical variable, because that's not numerical. It's a yes or no question. Does the house have air conditioning? 0 means no. No. 1 means yes. Yes, yes. So in this data set, we have 4 houses. 2 of them do not have air conditioning, and 2 of them do have air conditioning. All right? So that's what the data set might look like in Excel. Let's get rid of that so we can write what our equations might look like. Got to get my mitt back on here so I don't get chilly. So we're going to have an equation that looks something like house price equals beta naught. This is our population model, so I'm using beta naught, plus beta 1. And that was square feet was my first independent variable. And then plus beta 2 AC, because that's my second independent variable. And that guy right there, that's our dummy variable or categorical variable. Now what you can do is last time we talked about this, it can only take values of 0 and 1 like we just saw in the data set. So we can actually take this equation and write 2 equations with it. We could write a no AC equation, and that's going to be HP, house price, equals beta naught plus beta 1 square feet. Now let's think about this variable. Well, if the house does not have AC, then the value of AC is 0 in that equation. So that means 0 times beta 2 is what? Just 0. So I don't even have to write it in the equation. Now I'll also want my other AC equation. That's going to have HP equals beta naught plus beta 1 SF. Now, what is the value of AC in the does have air conditioning equation? So let's write yes here. Yes, AC. So in this equation, this is for the houses with air conditioning. Well, air conditioning takes on a value of 1 at those houses. So we don't even have to write AC again, because 1 times beta 2 is what? It's just beta 2. So that's what's nice about having these special categorical variables that can only take 2 values. Well, we can just write out the equation for each of those 2 cases. The no AC version, where that just drops out of the equation, and the yes AC equation. And you remember back in the day, you had to do something called collecting like terms. Like terms are putting together parameters that do not have, oops, I lost my screen here. There we are. Oh, what's going on here? So putting together like terms is putting together parameters like beta naught, beta 1, and beta 2 that are multiplied by the same type of variable. So if you have 4x plus 5x, you can write that as 9x. But if you have 4x plus 5, you can't put those together. So the way we could think about that here is, well, beta naught, the intercept, is not being multiplied by a variable in this equation. Beta 2 is not being multiplied by a variable anymore now that we wrote out the SAC equation. So we can collect those together because they're like terms. HP equals beta naught plus beta 2 plus beta 1 square feet. And now we can really do a better job of comparing our yes AC equation to our no AC equation. Because what this shows is that this is just the new intercept term for the yes AC equation. The whole line will shift up. Notice that they have the same slope, beta 1 and beta 1. That's the slope for both equations. But with this independent variable, with this new AC 0, 1 variable, that allows the intercept to shift when they have AC, presumably up because people like having AC. So we're going to have a line that's shifted up as a result of having AC. So let's take a look at what that would look like if we graph these equations. So let's keep our main equation there. We want, see if we can get a better black marker right here. We want house price on that axis because that's our dependent variable. And we'll have square feet over here. Notice I'm using the numerical independent variable to draw this graph. And what we've done is we've allowed the intercept, so presumably we have an upward slope of house price in square feet. As square feet increases, house price increases. We'll call that the no AC equation. And notice this right here, this intercept is beta naught. Well, if having AC is valuable, then what we just showed is we're going to take that and add beta 2 to it. So right here, beta naught plus beta 2, boom, that's our new intercept. The lines are parallel. So we're forcing the change with square feet to be the same across the houses. And this is our yes AC equation. Now we might ask, is there a statistically significant difference in house prices that for houses that have AC and do not, holding square feet constant? Well, we can answer that question by doing a hypothesis test on beta 2. If we think that it probably increases house prices, then we're going to have greater than 0, because that means we're adding a positive number to shift up the line from air conditioning. And then, of course, our null hypothesis would be that there's no effect or it's actually negative. All right, so that's the math that underlies categorical independent variables. All right, I'll see you guys on the flip side.